Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to our 18th lecture of MTH108 Business Math 1. Today we will continue with our chapter 7, which is about exponential and logarithmic functions. What we have done in our previous two lectures of chapter 7, we have studied the properties of exponents and radicals. Then we have studied the definition of exponential functions along with some examples, and the classes of exponential functions, that is two particular cases when b is any base and when the b is a special number e, the irrational number e. Then we have seen the graphs of exponential functions for two different cases, when b is strictly greater than 1 and when b is between 0 and 1, and the characteristics of the exponential functions with the help of graph. We have also seen that given any exponential function can be converted to the base e by using a very simple rule. Then we have studied the logarithmic functions and the properties of logarithms. Using these properties of logarithms, we have solved the logarithmic equations. We have also studied the graphs of logarithmic functions, and with the help of graph of logarithmic functions we have defined the characteristics of the logarithmic functions for the two cases, again when b is greater than 1 and when b is strictly between 0 and 1. And we have also seen some applications of logarithmic functions in our previous lecture. Today we will focus on the applications of exponential functions, on some applications of logarithmic functions as well, and we will see that how we can solve our exponential and logarithmic functions in more detail. So let's start our today's lecture. First we see the applications of exponential functions. Now exponential functions have particular application to growth process and decay process. For example, growth process can be population growth, appreciation in the value of assets. They are all known as the exponential growth process. There can be many decay process, for example declining value of certain assets such as machinery, decline in the efficiency of machine. They are known as the exponential decay process. In both the cases, whether we have an exponential growth process or an exponential decay process, they are usually stated in terms of time t. We start with our example of compound interest. What do we mean by the compound interest? That is the interest earned by an invested amount of money is reinvested so that it too earn interest. That is, the interest is converted into principal and hence there is interest on interest. What do we mean by the compound interest in simple words? For example, you have put, let's say, 100 rupees in bank, and the bank says that after 1 year they will give you an interest of 5% of your original amount, called as the principal value. Then after 1 year you will receive your principal value will be equals to 105 by adding the 5% interest on it. What do you do with your 105? You put that 105 again in the bank for 1 year, and now you will obtain your interest on your new amount, which was 105 rupees. That is, now you are obtaining the interest on your amount which has already obtained the interest. So compound interest is nothing but we are obtaining the interest on interest. For example, if we have $100 invested at the rate of 5% compounded annually, that is, we have $100 and after 1 year we will obtain the 5% interest on our $100. So at the end of first year, if P is the principal amount, that is the amount which we have initially put in the bank or somewhere to obtain the interest. Initially the principal amount is 100 and we are given that the rate of 5% compounded annually. So if R is the increase rate per year, which is 5%. Okay, so this is our increased rate. Then after 1 year, if A will be the amount we will obtain, then after 1 year the amount we will obtain will be equals to our principal amount or the initial amount plus the 5% interest on our principal amount, that will be 5 by 100, and we obtain as that after 1 year we obtain the amount as 105, increased to 105. Okay, now after 2 years, if A is our amount, then A is equals to, now after 1 year our amount is increased to from 100 to 105. So after 2 years we will obtain the interest on this increased amount 105 with the interest rate same as 105 of as 5% of 105 now, and we obtain as 110.25. So in continuing in this way, we can obtain a formula which basically tells us that after, let's say, 5 years or 10 years, what will be the interest, compound interest on our initial amount. And the formula, general formula we will obtain will be no other formula than the exponential formula, which is now familiar to us. So after 2 years, the interest will be 110.25. Continuing in this way, if A is the accumulated or compound amount, then our compound interest will be compound amount minus the principal amount. For example, at the case of after 2 years, our interest will be 110.25 minus the initial amount, which was 100, and the interest after 2 years is $10.25. Continuing in this way, we have seen that we can find the compound interest after 1 year, after 2 years, and continuing in this way, we can find the general formula to obtain the compound interest, let's say after 10 years. Then more generally, if a principal amount of P dollars is invested at the rate of 100% compounded annually, then compound amount after 1 year will be, if P is the principal amount and the interest is P times the R, so after 1 year our amount will be equals to P into 1 plus R. After 2 years, we will obtain the interest on this new amount, which is P into 1 plus R. So after 2 years we obtain P into 1 plus R plus the interest on this amount, which is P into 1 plus R into R. And solving this, we obtain P into 1 plus R into 1 plus R, which is nothing but P into 1 plus R whole square. So this is the interest we obtain after 2 years. Continuing in this way, we can write our formula for the case of after n years. That is, after n years, the amount will be P into 1 plus R whole to the power n. That is, at the end of n years, the amount will be the principal amount into 1 plus the increase rate. Now, if we look carefully at our formula, we have an exponential formula, which is A is equals to the amount after n years is P into 1 plus the increased rate whole to the power n. And if we look carefully at our formula by comparing it with the general form, which is equals to A B to the power m x, we obtain that A is equals to P here, B is equals to 1 plus R, and m is equals to 1 here. Now, let's say, assume that our principal amount is $1,000 and the rate of increase is 8%, which is 0.08. Then after 2, and we are interested in knowing the amount after 2 years. That is, if n is equals to 2, our amount will be equals to, we will put the values in this formula. After 2 years, our amount, original amount 1000 into 1 plus R, which is 0.08, and after 2 years, so n will be equals to 2. Simplifying, we obtain 1.08 square, and taking the square and multiplying by 1000, we obtain 1166.4. We obtain 1166.4 is the amount after 2 years. Let's say we want to find the amount after 10 years, that is when n is equals to 10, then the amount will be equals to, we'll simply put the values of our principal amount, which is 1000, into 1 plus R with the same rate. We obtain 1.08, and now here n is equals to 10, and by simplifying we obtain that the amount will be equals to 2158.92 rupees or dollars, whatever the currency is. If we want to plot this, if we want the graph of this compound interest function, it is an exponential function, then initial amount was 1000. After, let's say, 2 years, it is somewhere here. After 2 years, after 10 years, if it is 2000, after 10 years, the amount is somewhat like this, and we will connect these dots to obtain the graph, which is like this, which means that in this case the graph is an exponential function, and the graph or the function is an increasing function, and the function is an increasing function. And what will be the compound interest? Compound interest is simply the difference of the amount minus the principal value, that is the difference of 2158.92 minus the principal value, which was, so we can find the compound interest simply by taking the difference of the amount after, let's say, 10 years with the original amount. Example of compound interest we can consider in more detail. That is, when the compounding of interest is more than once a year, then the previous equation can be rewritten as, if A is the amount, for example, if interest is quarterly, then the amount A will be equals to P into 1 plus R by 4 into 4T. Particularly if the principal amount is 1000 and the increased rate is, let's say, 5%, then after time t is equals to 1, the amount A will be equals to the principal amount into 1 plus 5 by 400 whole to the power 4, which is equals to, after simplifying, 1000 into 1.05, and we obtain 1050.94. So this is the formula of continuous compounding, or when the interest is more than once a year. But if the interest is continuous, for example, when compounding of interest is continuous, means compounding is occurring at all the times, that is, there are infinite number of compounding periods each year, then our function will be equals to, A will be the function of time, will be equals to the principal amount into exponential of our increased rate into time t. For example, if our interest is 8% and the time is 10 years with the initial amount same as P is equals to 1000, then the amount will be equals to 1000 into exponential of 80 over 100, and simplifying we obtain that 100 in 1000 into 2.225, and the interest, continuous interest, is 2225.5. If we want to compare this continuous compounding with the annual compounding, we have solved this particular case for time t is equals to 10 years and when the increase rate is 8%. We obtain that from the annual compounding, it was 2158.92, initially starting from 1000, which is this graph. This is the graph of annual compounding. Continuous compounding will be starting from the same point and like this. So this is the graph of principal amount into exponential of RT, that is the continuous compounding. And this is the graph of P into 1 plus R to the power N. So now we have seen that there is a slight increase when there is a continuous compound as compared to the annual compound, and we can reformulate our compound function, compound interest in terms of the exponential function, and we can easily find the amount of compound after some particular period of time. Next example is of population model, which we can define exponentially. Consider a general function of the exponential growth process. V is equals to f of t is equals to v naught e to the power kt, where v is the value at time t, v naught is the initial value, and k is the growth constant. For example, if p is equals to 100 in 1970, then our population model will be equals to v is equals to 100 into, and if further our k is equals to 0.04, that is 4% per year, then our population model will be equals to 100 into 0.04 t. Now in 1995, t is equals to 25, then our population model will be equals to v is equals to 100 e to the power 0.04 into 25, which is equals to 100 into e, which is equals to 271.83. And if we want to plot the graph of this population model, this is 100, then our graph will be like this, which is an increasing function. We are further asked that how long will it take for the value of the function to increase by some multiple, where our population model is v naught e to the power kt. Since this is a growth model, so k is positive. And we are asked that how long will it take when the population will be equals to double, that is the 2 times of the initial population. By putting this value in our population model, we obtain 2v naught is equals to v naught into e to the power kt, which implies 2 is equals to e to the power kt. Now since our k is 4%, we obtain 2 is equals to e to the power 0.04 t. Now from the calculator and table we know that 2 is equals to e to the power 0.69, which is e to the power 0.04 t. This gives us 0.69 is equals to 0.04 into t, and by solving this we can find the value of t, which is approximately equals to 17.25 years for the population of a community to be double. Now we consider one more exponential function, which is about the decay process, that is the price of a machinery. Consider the general form of the exponential decay function as it is same as our growth function, with v is equals to the initial value, v naught is the v is equals to the value at time t, v naught is the initial value, into e to the power minus kt. Since this is a decay model, so k is negative. V is the value at time t, v naught is the initial value and k is our decay constant. For example, if our initial value is 100 and our decay constant is 1%, which is 0.01, then our decay model will be equals to v is equals to 100 into e to the power minus 0.01 t. We are asked to find the value at time t is equals to 5. Then we will simply put the value of v in our decay model, which is equals to 100 into e to the power minus 0.01 into 5, which is equals to, after simplifying we obtain 95.12. For example, if we are further asked to find the value after 10 years, that is when t is equals to 10, then v will be equals to 100 into e to the power minus 0.01 into 10, which on simplifying we obtain 90.4. And the graph of this function will be, if this is 100, this is, let's say, 90, and in between is 95, and on our x-axis this is 5 and this is, then the graph will be a decreasing function. Since this is the model of decay process, so the graph is naturally a decreasing function, that is falling from left to right. Now we consider the applications of logarithmic functions. If we are asked to find the population growth, recall that our exponential function for this case was v is equals to v naught into e to the power kt. Since this is a growth process, so k is positive, and when v is equals to 2v naught, our model becomes 2 is equals to e to the power kt. Now here we can use our log property. In the case of exponential growth, we have put the value of 2 is equals to e to the power 0.69, that is, we have converted 2 to the base e and simplified our equation. But here we can take log, natural log on both sides, and we obtain natural log of 2 is equals to natural log of e to the power kt. This natural log with the base e cancels out and we are left with kt. Now if the growth rate is the same as 0.04, which is 4%, then the time t will be equals to natural log of 2 divided by 0.04, which is equals to 17.32 years. If we compare this result with the previous slide, as the population model solved with the help of exponential growth, we obtain that the population will double after 17.25 years, and we have solved the same population model with the help of our logarithmic function, and we have obtained that after 17.32 years the population of that community will be doubled. So by using the property of log, we can easily simplify the value of time after which some amount will be doubled or half or increased or decreased. Okay. If we are asked to find that the time when the population will be triple of the initial population, then we will put this value of v in our population model, that is 3v naught is equals to v naught into e to the power kt, and we obtain 3 is equals to e to the power 0.04t, where k is the same as in the previous example. Now by taking the natural log on both sides, we obtain that natural log of 3 is equals to 0.04t, and we can simplify this to find the value of time, which is equals to natural log of 3 over 0.04. And after 27.46 years, the population of the community will be tripled. Similarly, we can use this equation, the decay equation, v is equals to v naught into e to the power minus kt. K is negative, so this is a decay process. And if we are asked to find the time t when the population or the amount is reduced to half, that is when v is equals to half of the initial value, then we can simply put these values in our equation with our decay rate k, and we can find the time t in which the initial value is reduced to half. That is we recall our equation v is equals to v naught e to the power minus kt of the decay model. And suppose the amount of radioactive substance is reduced to half, that is v is equals to v naught by 2, when the decay rate k is equals to 4%, which is 0.04. Then we are asked to find the time t in which the amount is reduced to half. So by putting the value of v is equals to v naught by 2, we obtain v naught into e to the power minus 0.04 t, and simplifying we obtain 1 by 2 is equals to e to the power minus 0.04 t. Now again, by taking the natural log on both sides, we obtain log of 1 by 2 is equals to minus 0.04 t. And now here we can use the property of natural log, that is natural log of 1 minus natural log of 2 is equals to minus 0.04 into t. Since log of 1 is 0, we are left with minus log of 2 is equals to minus 0.04 t. Minus sign also cancels out, and the time t will be equals to log of 2 over 0.04, which is approximately equals to 17.32 years. That is, after 17.32 years, the amount of the radioactive substance will be reduced to half of the original amount. Now we will solve the logarithmic and exponential equations using the properties of exponents and the log. We recall that a logarithmic equation is an equation that involves the logarithm of an expression containing an unknown. For example, log of x plus 4 is equals to 5. An exponential equation has the unknown appearing in an exponent. For example, 2 to the power 3x is equals to 7. Now in many functions, if f of m is equals to f of n, then this does not imply that m is equals to n. For example, if we have our function as quadratic function x square, then f of 2 is same as f of minus 2, but the numbers are totally different. However, in log and exponential functions, these properties hold. That is, if log of m to the base b is equals to log of n to the base b, then those numbers are basically equal. We have already used this property and the same property for the exponents in our previous examples, but now we will see these properties in detail. And the property for exponents is that if b to the power m is equals to b to the power n, this means that the exponents are same. Now we will use these properties to solve our logarithmic and exponential functions. For example, we are asked to find x if 25 to the power x plus 2 is equals to 5 to the power 3x minus 4. To solve this exponential equation, we have to use our properties of exponents or logs to find the value of x. How we will find the value of x? Okay, if we look at the left side of our equation, 25 is nothing but the 5 square whole to the power x plus 2, which is equals to 5 to the power 3x minus 4. Now by using the property of exponents, we obtain that 5 to the power 2 into x plus 2 is equals to 5 to the power 3x minus 4. And now by using the property stated above for the case of exponents, that is, same base have different powers, means the powers are also same. So this gives us that 2 into x plus 2 is equals to 3x minus 4. Now this is nothing but a linear equation in one variable x, and we can easily solve this linear equation to find the value of x, which satisfies our exponential equation. Simplifying this, we obtain 2x plus 4 is equals to 3x minus 4, and we obtain x is equals to 8. So x is equals to 8 is the value which satisfies our given exponential equation. Now we will solve one more equation containing both exponents and the logs. We are asked to solve 5 plus 3 into 4 to the power x minus 1 is equals to 12. Now the exponent is only on 4 and not on 3. Okay, then we will first simplify it as 3 into 4 to the power x minus 1 is equals to 7, and 4 to the power x minus 1 is equals to 7 by 3. Now taking the log on both sides, we obtain log of 4 to the power x minus 1 is equals to log of 7 by 3, which is by property log of 7 minus log of 3. And on the left side we will use the property of exponents, that is, we obtain x minus 1 into log of 4 is equals to 1.945 minus 1.098, and we obtain x minus 1 is equals to 0.847 over 2 log 2, which is nothing but log 4, which is equals to 0.611. And further simplifying, we obtain x is equals to 1.611. So this is the value of x which satisfies our given exponential equation. Now using these exponential equations and the properties or methods to solve these exponential equations, we will solve some word problems. Now first we have a problem of oxygen composition. An experiment was conducted with a particular type of small animal. The logarithm of the amount of the oxygen consumed per hour was determined for the number of animals and was plotted against the logarithm of the weights of the animals. That is, on one side we have the log of the amount of oxygen consumed, and on the other side we have the log of the weights of the animals. And it was found that log of y is equals to log of 5.934 plus 0.885 log of x, where y is the amount of oxygen consumed and x is the weight of the animal. And we are asked to find the value of y. That is, we are asked to find the amount of oxygen consumed when we are comparing it with the weight of the animal. Okay, let's rewrite our equation as log of y is equals to log of 5.934 plus 0.885 log of x. Okay, first we will simplify our logs. How? We have log of y is equals to log of 5.934 plus, here we have some product or multiple of logs, so it will be simply written as the exponent, that is the log of x to the power 0.885. Now we can use the second property of logs, that is we have sum of two logs. This can be combined, written as log of the product. So log of y is nothing but the log of the product 5.934 into x to the power 0.885. And now taking the anti-log on both sides, or the log of two things is same, equal, which means that two numbers are also equal. So y can be written in terms of x, which is the weight of the animal, as 5.934 into x to the power 0.885. So this is our equation in unknown variable y when the weight of the animal is known, which is x. We know that the demand equation depends on the two variables, that is the price and the quantity demanded. So the demand equation for the product is, let's say it is P is equals to 12 to the power 1 minus 0.1 Q, where P is the price and Q is the quantity demanded. And we are asked to express the quantity demanded in terms of price. Okay. So where P is the price and Q is the quantity demanded. Now what we will do, we will simply take the log on both sides, that is the log of P is equals to log of 12 to the power 1 minus 0.1 Q, and now this power will come as the multiple, that is 1 minus 0.1 Q into log of 12. And okay, so now we have our log of P is equals to 1 minus 0.1 Q into log of 12, and we can write it as log of P over log of 12 is equals to 1 minus 0.1 Q, or log of P over log of 12 minus 1 is equals to minus 0.1 q, and we obtain q is equals to 1 divided by 0.1 into 1 minus log of p. Let's take one more example. We are asked to solve 10 to the power 2x is equals to 3. That is, we are asked to find the value of x which satisfy this equation. We will simply take the log on both sides, that is log of 10 to the power 2x is equals to log of 3, and since the base and the number is same, so this cancels out and we are left with 2x is equals to log of 3, and x is nothing but log of 3 over 2, which is 0.2386. So now we have seen few examples of exponential and log functions in which we can use the properties of exponents or log to find the value of the unknown or to rewrite the equation in the explicit form, that is in the form of dependent variable appearing in the form of independent one. If we look at our last example, 10 to the power 2x is equals to 3, in order to solve this exponential equation, we have used the properties of log to simplify it, and we can easily find the value of the unknown x. Now consider one more application of the log function, which is the predator-prey relation. Consider an equation of the form y is equals to k into 1 minus e to the power minus a x, where x is the prey density, y is the number of prey attacked, and k and a are constants. And we are asked to show that natural log of k over k minus y is equals to e to the power ax. How we will show this? By using our equation y is equals to k into 1 minus e to the power minus ax. Our aim is to eliminate e to the power ax on one side. So we obtain y over k is equals to 1 minus e to the power minus ax, and simplifying y over k minus 1 is equals to e to the power minus ax minus e to the power minus ax, or simply e to the power minus ax is equals to 1 minus y over k. Now what would be our next step? To take the natural log on both sides. We have our equation as e to the power minus ax is equals to 1 minus y over k, which is capital K minus y over k. Now taking natural log on both sides, we obtain natural log of e to the power minus ax is equals to natural log of k minus y over k. The natural log cancels out with our base e, and we are left with minus ax is equals to natural log of k minus y over k. Now we will multiply minus 1 on both sides. In fact, we will use the property that natural log of 1 over m is equals to minus times natural log of m. So on the right hand side, what we are doing, we are using this property, which is minus times natural log of k over k minus y. the minus sign cancels out and we are left with ax is equals to natural log of k over k minus y. So by using the properties of log functions and exponents, particularly the log functions, we have proved the relation that if we are given with the equation y is equals to k into 1 minus e to the power minus ax, we can use this form e to the power ax is equals to natural log of some function by using the properties of log. Let's consider one more example. Okay, we are asked to solve the equation log of x to the base 2 is equals to 5 minus log of x plus 4 to the base 2. And we are asked to solve this logarithmic equation, that is we have to find the values of x which satisfy this equation. Okay, now what would be the solution? We have to assume something on x, that x should be positive and x plus 4 should be positive. Why? Because if x is equals to 0, then log of x is undefined, and if x plus 4 is equals to 0, then log of x plus 4 is also undefined. So in particular we have assumed that x should be positive. Now we will rewrite this equation as log of x to the base 2 plus log of x plus 4 to the base 2 is equals to 5. Now we can use the property of logs, that is log of product is equals to sum of logs. So this can be written as log of x into x plus 4 with the base 2 is equals to 5. Okay, now taking the exponential form of this log function, where we have that if we have the exponential form y is equals to b to the power x, this is equivalent to x is equals to log of y to the base b. Then here y is equals to x into x plus 4, x is equals to 5, the base b is equals to 2. This can be written in the exponential form as x into x plus 4 is equals to 2 to the power 5, which is 32. Now we will solve the left hand side, which is x square plus 4x minus 32 is equals to 0. This is a quadratic equation or second degree equation in one variable, so we will use the factors, or we can also use the quadratic formula to solve this equation. Here we will use the factors, which are x square plus 8x minus 4x minus 3 is equals to 0, minus 32 is equals to 0, and we obtain that x into x plus 8 minus 4 into x plus 8 is equals to 0. Simplifying, we obtain x minus 4 into x plus 8 is equals to 0, and the values of x are x is equals to 4 or minus 8. But we were given some condition on the values of x initially, that x should be positive and x plus 4 should be positive. So the value of x is equals to minus 8, this rules out, and we are left with x is equals to 4, which satisfy this logarithmic equation. We can also verify this by putting the value of x in our given logarithmic equation. Our log equation was log of x to the base 2 is equals to 5 minus log of x plus 4 to the base 2. Now we have to check that for x is equals to 4, the root which we have just found by using the factorization method, does this value satisfy our logarithmic equation or not? So we obtain the left hand side is log of 4 to the base 2, and the right hand side is 5 minus log of 4 plus 4 to the base 2. Left hand side we can write as log of 2 squared to the base 2, and by using the property of exponents it will be equals to 2 times log of 2 to the base 2. Now the right hand side will be equals to 5 minus log of 8 to the base 2, which will be equals to 5 minus log of 2 cube to the base 2, okay, which can be further written as 5 minus 3 log of 2 to the base 2. Now log of any number with the same base is equals to 1, so this is equals to 1 and this is equals to 1. So on the left hand side we are left with 2, and on the right hand side we are left with 5 minus 3, which is 2. So x is equals to 4 satisfies our given logarithmic equation. Now we have seen enough examples of logarithmic equations and the exponential equations, and by using the properties of exponents or the properties of log we can solve our logarithmic equation or the exponential equation, or we can easily convert our logarithmic equation into the exponent form to solve it more easily, and vice versa. We have also seen some examples, some word problems where we can use the log function or where we can approximate our real world problem with the log function. With this we end our today's lecture. What we have studied in this lecture so far: in this lecture we have studied the properties of exponents and radicals, then we have studied the exponential functions and the classes of exponential functions. That is, the particular case is when the base b is equals to the irrational number e. We have also studied the graphs of exponential functions when the base b is greater than 1 or when the base strictly lies between 0 and 1. If we are given an exponential function in any base, we can easily convert it to the base e, and we have also seen it in our examples. We have studied the definition of logarithmic functions along with some examples, the properties of logs, and we have used these properties to solve the logarithmic equations. Further, we have studied in this chapter the graphs of logarithmic functions. With the help of graph of logarithmic functions, we have given the characterization of the logarithmic functions and some applications related to the log functions. Further, we have also seen the applications of logarithmic functions, exponential functions, and the log and exponential equations, where we have used the properties of logs and exponents to simplify for the unknown variable. With this we end our today's lecture, and in our next lecture we will start our next chapter about matrix algebra. Allah Hafiz, students.